Have you ever stared up at the night sky and felt a profound sense of wonder? Have you ever considered that everything you see, every star, every galaxy, every wisp of cosmic dust, might be just one page in an infinitely large book? What if our entire universe, with all its billions of years of history and its unfathomable scale, is just a single bubble floating in a vast cosmic ocean of other bubbles? This isn't just a question for late-night dorm room conversations or science fiction movies. It's a question that physicists, cosmologists, and astronomers are grappling with right now at the very edge of human knowledge. The possibility is as humbling as it is mind-bending. The implications of this idea are staggering. Imagine a reality where every choice you ever made spawned a new universe. Fasten your seatbelts. The universe, or universes, are waiting. So what exactly is a parallel universe? The term gets thrown around a lot often, conjuring images of evil twins with goatees. But in physics, the concept is more subtle and varied. At its core, a parallel universe is another self-contained reality that coexists with our own. It's a separate space-time. Think of it like houses on a street. Your house is your universe rooms rules family. The house next door is a parallel universe. You know it's there, but you can't just walk through the wall. There isn't just one single theory. It's an umbrella term for several scientific ideas from different branches of physics. Version 1, universes like ours but unimaginably far away. Version 2, quantum mechanics, constant branching with each quantum event. Version 3, string theory, our universe as a brain in higher dimensional space. One of the most compelling arguments for a multiverse comes from a theory called cosmic inflation. This isn't some fringe idea. It's our leading explanation for why the universe is so big, so uniform, and so flat. The theory goes like this. In the very first fraction of a second after the Big Bang, the universe underwent an astonishingly rapid and violent expansion. It grew from smaller than an atom to larger than a galaxy in a sliver of a moment. This inflationary period stretched out the fabric of space-time, smoothing out any initial wrinkles. It's like boiling a pot of water. Bubbles of steam form and expand. The theory of eternal inflation suggests that while inflation stopped in our region, our bubble cooled, new bubble universes keep forming, each one pinching off and evolving on its own. Each of these bubbles could cool down with slightly different physical properties. With an infinite number of bubbles, it becomes statistically inevitable that some, like ours, would have the just right conditions for stars, planets, and life to emerge. Let's shrink down from the cosmic scale to the bizarre world of the infinitesimally small. Here, things are governed by the strange rules of quantum mechanics. In this realm, particles like electrons can exist in multiple places at once, superposition. They only choose a single location or state when we measure them. Why does the act of observation force reality to pick a single outcome from a sea of possibilities? The many worlds interpretation first proposed by Hugh Everett III in the 1950s offers a radical answer. Everett suggested the particle doesn't choose one path. At the moment of measurement, the entire universe splits. Reality branches into multiple copies. In one universe, the electron is here. In another identical universe, it's over there. This happens for every single quantum event every moment of every day. You are constantly splitting into countless versions of yourself, each living in a separate parallel universe. For a long time, the multiverse was purely a theoretical concept, a consequence of our equations, but seemingly untestable. That might be changing. As our instruments have become more sensitive, we've begun to scan the cosmos for clues for anomalies that don't quite fit our standard model of a single universe. One of the most tantalizing and controversial of these clues is a feature known as the CMB cold spot. It's a vast, unusually cool patch in the cosmic microwave background radiation, the ancient light from the Big Bang that fills our entire universe. Discovered in 2004 and confirmed by subsequent observations, the cold spot is enormous, over 1 billion light-years across. Within our standard cosmological model, a fluctuation of this size and coldness is extremely unlikely. While it could just be a random fluke arrangement of matter and energy in the early universe, some cosmologists have proposed a much more exotic explanation. They suggest the cold spot could be a bruise left on our universe from a collision with another bubble universe. It could be the first observational evidence of the multiverse. If two bubbles bumped into each other, the collision would have rattled our young universe, creating a disturbance, leaving behind a slightly colder, less dense area that stretched over billions of years into the cold spot. Scientists are testing this idea. Some studies find support, others find alternative explanations like a supervoid. The debate continues. Our cosmic exploration now takes us to the cutting edge of theoretical physics, string theory. This is an ambitious attempt to create a theory of everything, uniting general relativity with quantum mechanics. The central idea is that fundamental particles are tiny, vibrating, one-dimensional strings of energy. Different vibrations give rise to different particles, like different notes on a guitar string. But for the math to work, extraspatial dimensions beyond the 3 we experience are required. The theory posits possibly 10 or 11 dimensions in total. These extra dimensions are thought to be curled up, compact and too small to perceive directly. In the brain world hypothesis, our universe is a membrane, a brain, floating in a higher dimensional bulk. There could be other brain universes floating parallel to ours, perhaps a microscopic distance away in a 4th spatial dimension. We are stuck to our brain, like water droplets on a shower curtain. We can't directly cross. Most forces and particles are confined to their own brains, but one particle might be an exception, the graviton. If gravitons can leak between brains, gravity could be leaking into other dimensions, explaining why gravity is so weak compared to other forces. Particle accelerators like the LHC search for missing energy or heavy particles that could indicate energy escaping into extra dimensions. If energy vanishes from collisions in ways we can't explain, it could hint at extra-dimensional leakage. Future gravitational wave observatories might even detect faint tremors from brain collisions. These are speculative ideas, but they give us testable predictions, and experiments are underway. So after this journey to the edge of reality, where do we stand? Do parallel universes exist? The honest answer is, we don't know for sure. There is no single photograph or definitive piece of data that says, here lies a parallel universe. What we have is a collection of compelling clues, a series of tantalizing breadcrumbs laid out by our most successful scientific theories. Ideas like eternal inflation, the many worlds interpretation, and brain cosmology all emerge as logical consequences of the mathematics that so accurately describe our own universe. We are in the early days of a grand cosmic detective story. Cosmic inflation predicts a multiverse, and its predictions for our universe have been confirmed with great precision. Scientists will continue to scrutinize the CMB for collision signatures like the cold spot, search for missing energy at the LHC, and build next-generation gravitational wave observatories to look for faint ripples. The search is on, and our tools improve every year. Whether the multiverse is real or not, investigating it expands our understanding of reality. The story is far from over. In fact, it may have just begun.